The next meeting is going to be 2 weeks from now, and I will be reaching out to some of you who volunteers to do your presentations. And hopefully I understand the first one may not be perfect, but hopefully through trial and error, we're going to make this work. We're a diverse group of people, diverse geographically, primarily, and we do different things as well. So this would have been difficult even if we were in the same institution facing face to face. It's going to be much more difficult now that we have to do this electronically, but I hope that if everybody is invested in this, it's going to happen, it's going to work well. So just to move forward, one thing, we'll be reaching out to each one of you soon to get a list of people that, and emails that you want to be contacted anytime there's an announcement with respect to seminars. So remember, wait for this to happen from ZISIS. And a bit of update for what's happening with the network. We're now, in terms of the paperwork, we're about to send out the second round of, the second version of the network agreement for reviews. There is some internal discussion with some of the groups that had raised concerns the first time around, and I hope that within a week or two we're going to be able to send that out to everybody. That's in terms of bureaucracy. So thank you everybody, and thank you Tor for making time today. Thanks.
You guys hear me now? Hopefully you can.
Yes.
And then I'll just move this out of the way so you guys can see my slides. And if people have questions, I guess there's some sort of chat channel that you can type those in, and hopefully those will get relayed on to me. All right, so I'm going to talk about my past research and ongoing research on hardware accelerators. So just a bit about me. I'm a faculty member here at UBC, and I've been here since 2006. My research is mostly on computer architecture, most recently focusing on accelerators for machine learning, naturally. Prior to that, and still currently, on architecture for GPUs for compute. I spent about almost a year at Stanford CS department on sabbatical back in 2012, 2013. I got all my degrees at U of T. I did my undergrad in engineering science and the EE option. Some interesting curiosities. I swam varsity swimming for 2 years and then got sidetracked with studies. I did a co-op at Allied Signal Aerospace, which was, the further I go from that co-op, the more I realized I learned a lot. At the time, I didn't think I was learning anything. My PhD in computer architecture, did an internship at Intel. Prior to joining UBCA, I was at NVIDIA for about a bit over almost a year and a half, not a bit under that. I worked on the first GPU that supported CUDA, which is the C-like programming language that people use to write machine learning type kernels on GPUs. I'll tell you, back then they had no idea that this stuff was going to be used for machine learning. I can confidently say that. Other things, curiosities, being a Canadian, I did Shad Valley, which is this thing for high school students. I did Air Cadets, and my first job was at Shopsies. All right, team here. So these are the students nominally working on Cohesa at UBC in my group. Amruth, who is sitting behind me, who you got a good shot of in the video. Nagar, Amir, who's also here, and then Dave Evans. So Amruth is second year master's student. Nagar just starting her master's degree here. Amruth, I should say, was from MIT. Nagar is from Sharif. Amir is from one of the IITs. He's also just starting his master's degree, but actively working on research along with Nagar. And Dave is a PhD student, and I like to think of him as like a particle in Brownian motion. And he's been working on all kinds of topics, and now he's working on Cohesa stuff. Okay, so my past research, one of the things I'm well known for is a simulator of a GPU called GPU Sim. We've done a bunch of interesting stuff with it, looking at the impact of hardware scheduling on cache performance. Another thing that we've been doing recently is looking at how to support the execution models, single instruction, multiple threads on GPUs to make it more flexible, and particularly when it involves interaction. So software synchronization. There's a lot of interesting, subtle, tricky challenges there. So we've published a bunch of papers on that. And then, recently been working with Andreas and Natalie at Toronto on stuff related to accelerators for machine learning. So those are convolution and stripes. So one of the first things I did when I got here after working at NVIDIA is I said, they're not doing enough research at NVIDIA. We need this is a whole new topic and no one's exploring it. So the first thing you need to do that is a simulator, start developing one, back around 2007, development even earlier than that. What does it do? It simulates a GPU. It's configurable, so you can simulate different types of GPUs. And it's focused on just compute, so up to now, not graphics. It has a microarchitecture model of a compute core, caches, and a detailed model of DRAM. It's, as far as I know, the most widely used simulator for GPU architecture research. As of today, cited 1,031 times. It includes an energy model, which is increasingly important for research, for hardware research that looks at energy as well as performance. And it's been incorporated into many other simulators as when it was becoming increasingly popular that integrates a CPU model with GPU sim. If you look under the hoods of what are we actually modeling, we've got a fairly detailed model. This picture here is showing one core out of maybe 30 cores inside of a GPU, and this is the pipeline model, and there's various schedulers and other details in here, which I won't get into. Why do people like it? Well, one of the things is we've actually tried to see how close we are to existing hardware. So this figure down here shows a calibration study we did many years ago. At that time it was a current GPU. It's not current anymore, so not that relevant. But back then we were pretty well correlated with them. I think this is around 95 or 96% correlation. Each one of these dots is a different application. The x-axis is instructions per cycle on hardware, and the y-axis is instructions per cycle later. Always this good depending on what you're doing. There could be some outliers. And in more recent hardware, we still have to, one of our ongoing missions is to calibrate with more recent hardware. Reviewers tell us that we need to do this all the time. Some of the research that we published with GPU Sim, with synchronization, I'm not going to go through this bigger, but there's an interesting thing that happens if you take a parallel application written for CPUs and you just try to run it on a GPU. If that application involved any kind of communication between threads, you can get what we've called SMPTE deadlock. NVIDIA's most recent hardware, interestingly enough, Volta, is got some major changes in how SMPTE, single instruction multiple thread, is implemented that tries to address this. And I still think that maybe some of our research in this area we think it might have influenced them. Okay, so other things we're doing in the pipeline that's hopefully going to get submitted soon. We're looking at how to make GPUs grow up. CPUs are fully independent and they can do whatever they want. GPUs have always been tethered to CPU. And so with trends like disaggregated rack scale computers and the growing data centers, we think it's time for GPUs to become more independent. Not completely independent, just like a teenager, independent enough to take their car and drive out for, go on a date or something, but they have to come home for a curfew. Anyway, so how do we do this? So we're looking at support and extending dynamic parallelism hardware on GPUs. And so, of course, more exciting details will be published hopefully very soon. Here's some work that's not GPU related and not machine learning related, but it's related to interesting trends in architectural land related to energy efficiency. This is a paper we're going to present very soon at an FPGA conference, looking at how to change FPGA architecture, specifically. You can see the title up there. I don't know if you can or not, but specifically for the data center. So what we're looking at here is how to FPGA architecture. If you know what you're going to do is high-level synthesis from C code and run that on and synthesize that down to an FPGA, much like some of the stuff that's been published and discussed by Microsoft for Catapult. And so the question is, FPGAs were not architected for that, and so what would you change? And one of the things we found that you might want to change is add special fixed function blocks for state machines. And this is some data at the bottom showing that actually works pretty well. Another thing that we've been doing for many years is industry has told us that people actually buy GPUs to run graphics. Surprisingly, academics seem to have lost sight of that. So we've been trying to use SIM to support graphics with full Android emulation, and this is very close to being ready to ship so that people can start using it. We've got actual OpenGL Android environment. This is, as I said, it's been on project initially started with Qualcomm funding, and then most recently Google has actually chipped in some nice funding, and Ayub, who's up here in the corner, has been on internship, and they're supposed to send him back any day now, and can't wait for him to do that. Research we've done, we looked at, the motivation, of course, is if you look at the bottom here, performance of CPUs is stalling. If you go over 3 years, you're maybe 30% better. So this is work with Andreas, looking at, where does time go in a convolutional net, and this was with Natalie as well. And we said, are we discovered, or we made the same observation maybe many people have made, is that 90% of the time for convolutional nets was going to dot products. And so, what's a dot product? It looks like this. One of the things that we found, the inputs to these dot products are zeros. And so the idea that we had was, well, take convolution and get rid of the zeros, so you get this convolution, which nobody knows how to pronounce, and basically you skip all the zeros. And that helps, performance by about 50% with some small increase in area. Now, and this is sort of much more Cohesa related, is we're looking at how to improve the training speed of deep neural networks. So this is Amruth, who was the one who's in the center of the photo, who I don't think you can see right now, though. And the motivation really is how to make faster training, and we're starting out by just taking the approach of just studying networks and looking at the software and looking for inefficiencies, any redundancy we can. While we were thinking of this, somebody published at ICML 2017 something very close to the ideas we had called MEPROP. And so my, one sentence summary of MEPROP is not all weight updates are created equal. That's a one sentence summary. And I guess our research program here is what other opportunities like this exist. We're currently, MEPROP focuses on the back propagation pass. Ambrose is currently focusing on the forward pass. And he's very excited. We've got some CPU-only results showing that we can go 2.4x faster on a CPU. On the GPU, because it's a GPU and GPUs have, little intricacies, we're only about 14x faster if we do a proper fair comparison instead of the one that Amruth wants. And you know what? I think that's all I have, and I don't have even a final slide. So I just got end of slideshow here. Let me see if I can switch back to my other thing, and other people can see us. Okay, I'm done. That's it. That's my little short. So any questions? I can answer questions.
So thank you, Tor.
Yep.
For the time being, I understand this is not the very best way of doing things, but if you have any questions, please, if you're in the room, of course, you can ask. And there are several people in the room. We can probably rotate the camera later on to show how we're here. But we have several people online. Next time, we'll try to have a landline where you can call and actually do ask questions the normal way.
Right.
But for the time being,
Right.
so for today, if you have any questions, please post them on the YouTube page, and we're going to relay them to Tor. Or Tor can see them himself.
I can't see anything. Well, let me see. Yeah, maybe I can. Let me, okay. If you can put them in the Skype chat here, then I can read them. Maybe you can cut and paste them or something. No questions.
That's okay. I mean, it's first time, right? It's expected.
Perfectly clear. or not at all interesting.
Well, if you have any suggestions for the format here, any ideas, you can email Zisis and myself, or we can use this 5 minutes we have left today to do that. Otherwise, we'll move ahead and meet 2 weeks from now. We'll be there, 27, correct. Anything?
We have a question.
Yay.
We'll have to wait for it. Okay, so we have a question from Chris Powell. I can relay the question if that's okay. So, Tor, how practical do you think it would be to implement this zero avoiding strategy on existing GPU architectures?
Yeah, I guess in some sense this is kind of what we're trying to do right now. So the stuff that Amruth, who's right here, has been working on is we're looking at paper, if that's the one that Chris is referring to. But it's it was motivated by those observations that there were a lot of zeros, and so what we've been looking at is how the data that we have currently GPUs, you can get much higher speed up on a CPU, but of course that's really slow to begin with. So I mean, I guess stay tuned. Hopefully, Amruth will get that 3x speed up on a GPU any moment now. Actually, I don't see, based on the data he has, I don't see why we can't get probably 2x improvement. Okay, maybe I should think about that more carefully before I promise 2x, but yeah. I hope that answers the question. I don't know if there's a follow-up.
If I can comment on that too, it's not about NVIDIA also is following, and Tor can chip in on this, they're following a dual strategy now. They are going to be optimizing, from what I understand, the GPUs to do ML well, but they're also deploying specialized designs for ML specifically that are GPU inspired, but they're very, very specialized to ML. So they have this, what's the name? Anybody remembers? They have this, they did release the Verilog for an accelerator that anybody can use if they want to, and I'm sure they're going to be building chips out of that. That thing skips weights and activations completely. And if there is interest, we can probably do a seminar on that. There is a paper last year on ISCA called SCNN that describes how they designed hardware specifically for exploring sparsity both in the weight and the activation of the range. So there's this duality there. It's not necessarily on the GPU.
So I guess the one thing though is that's for inference, right? The SCNN.
Yes.
This is asking about training or inference.
So it's inference.
But Chris's question, I guess, I'm not sure whether he was asking about training versus inference. Yeah. Being a machine learning researcher, maybe he's more interested in training times for his next paper, for example.
We have another question as well from.
There was also a follow-up from Chris. Maybe you want to read.
Yeah. All right. Yeah. So Chris is following up, and the question is: can you not just make it easy for threads to simply just not execute? This seems pretty feasible.
Amruth is laughing because it's actually very hard. I don't know if I have a great slide in my slide deck, unfortunately, to show this. Well, let me go back to a picture of hardware anyways, because it'll... Okay, so in this pipeline, the thing to keep in mind, this is the hardware pipeline, so I don't know how much familiarity people have with hardware here, but instruction goes through each stage here at a time. In a GPU, what's different is effectively you have 32 threads in each of these stages at the same time. And in particular, they all have to kind of be doing the same thing. So where it says here, SMT stack, this is where the rubber hits the road, so to speak. And there's a thing here called the active. So the active mask is which of the lanes in your GPU are actually going to do some work on this clock cycle. So the problem is if I look at a given neuron and I say, hey, this neuron isn't doing anything. If I look at how current software is written for training neural networks on GPUs, each lane in this active mask is actually responding to the neuron. And so when I get to this step where I'm going to issue the thread, I'll have some lanes masked off and some lanes are on. And so in that clock cycle, unless all 32 neurons are not doing anything, I have to issue that warp. I can't skip it. And so we actually find that if you just naively try to put in like an if statement or something, skip in there, you actually slow down your code, I believe. It's the latest result, which I now believe. So the trick there is, existing software has not been trying to exploit the sparsity, at least on the GPU. And so you need to rethink your software. So I don't know if I want to get into too much more detail since it's all super secret stuff. But, but that's the level of optimization that we're thinking about. Let's see if I can switch back here. Here we go. Hopefully that gives some insight into why it's a little bit more tricky than on a CPU. Was there another question? I think somebody said there was another question.
Yeah, there is another one by Arvind Shiraman. So the question is, any thoughts on ASIC versus GPUs for deep learning? For instance, Google said they moved training from GPUs to TPUs as well.
Yeah, well, that's interesting. So I don't remember, Arvind, whether you were at ISCA or not, and there was Norm Jeepy was presenting the TPU paper, and Bill Daly got up there, and of course he had to respond to it, and he, of course, did the standard NVIDIA complaint, which is you're comparing to our old hardware, not our new hardware. And Volta is so much better, and even Pascal was so much better, I think, than the thing they compared against. So I think, of course, he's the chief scientist, so he has to always defend the company. But, I think he tried to make the case that the GPUs are pretty close, right? It could be that when the TPU started out, GPUs were not being optimized enough, and maybe NVIDIA wasn't revealing to allay Google's fears that GPUs would get better at this. Or maybe Google just sensed an opportunity and decided to go after it. It'd be interesting. I'm sure NVIDIA would like to see an independent comparison done by academic GPU versus a GPU. Of course, you can't get a TPU because only Google has those. It's an interesting question. I guess fundamentally, you'd expect an ASIC can be better than a GPU. What's interesting about Volta is they've added something called tensor cores, which issues alone seem like interesting with the Google thing. Google's thing is called Tensor Processing Unit, and Volta, which is hardware that some people can get now, I don't think it's broadly on the market yet, has dedicated hardware in it, dedicated function units that are accelerating, and I guess presumably as efficiently as any tensor processing unit could do, at least for that block of hardware. And so, a year ago, I was thinking about doing, I've got some of the research we're doing, Amir is doing, and some of my other students are doing, is looking at how to have, such special function units. A year ago, I was thinking, if we were to publish this, we have to convince people that we're not adding any additional area penalty to an existing GPU that just does, say, graph. NVIDIA come up with this tensor cores in their Volta. It's how important machine learning is to the GPU space, that they're going to put dedicated hardware on there. And so, what is a GPU is really the question, I guess. I mean, it seems to evolve as the uses of it evolve, right? And so, what current crop of publications about hardware fixed function accelerators is you get more programmability, right? The TPU version 1, the one that was presented at ISCA this year, it is, as presented or as described in their paper, it is like a floating point unit, x86, 486, from Intel, right? Or 386. When you had the separate function unit and you had to buy that, you had to get a separate chip. If you had a 386, this is like going back to like the late, you wanted floating point, you had to buy a separate floating point coprocessor and your board, and you had to have probably a special motherboard too. That 486 integrated it, right? And now you wouldn't think of buying a CPU that doesn't have a floating point unit on it. It seems like with machine learning, we've made that whole leap in like 1 or 2 years from basically takes a long time to execute, and then now NVIDIA is going to have these special function units integrated right into their GPU. What is the difference going to be? And for data scientists working at like a Facebook or Google or wherever, the benefit of that special hardware, the ASIC hardware versus the flexibility you might have in an environment like a GPU, where does your engineering time outweigh on running the thing, right? You know, might be a case for inference and then for training networks to always use special function hardware. I think it's an open research challenge where you draw the line between flexibility and sort of fixed function there, which is, you know, presumably partly what we're going to study in this Cohesa thing. Anyways, I don't know. Those are my thoughts.
Right,
You know,
maybe
I'm not
we
that
should stop
formulated.
here today. I think because it's almost 2 o'clock. This is great. Really appreciate, first of all, Tor, for making time to do a quick overview and the discussion that's happening. I think there's a lot of interest now that's being shown, so maybe we should consider whether we should have a very short series of getting to know your hardware or getting to know your machine learning. I would certainly be more than willing to do a quick overview of, or maybe Tor can do that, or anybody else that's interested on what really happens under the hood when you execute things on a GPU, so people can better reason about what happens with their software. I mean, this is probably going to be like a 1 hour thing, and I've been teaching CUDA for quite some time. I'm sure Tor has been doing the same and others. Maybe we should start thinking about these ideas so we can quickly get everybody up to speed. So let's say au revoir for the time being. We're going to meet again in 2 weeks. I'll be reaching out to some of you to volunteer. And hopefully next time is going to be even better. So thank you all for attending today. Thank you, Tor, again.
Okay.
And
thank you.
see you in 2 weeks.